Hello again, cherubs. Okay, so hope you've had a relaxing Easter break and we are now back to it. Okay, so this is the second to last subtopic in this physics topic before we move on to something else. So, what we're looking at today is a half-life. Okay, now half-life, we'll get onto in a second, but what you have to remember is some key terms. All right, so we've already spoken about radioactive substances and how they behave, alpha, beta, and gamma radiation. All right, now how quickly unstable radioactive nuclei decay, all right, is what we are going to be looking at, and that is what half-life is essentially about. But there's two key terms that we need to look at. One is activity and one is half-life. Okay, so we'll look at activity first. Okay, so radiation in general is measured using a Geiger-Muller tube, or a GM tube, and a counter for short. Now, if you've ever watched any kind of movie where there's anything to do with radiation, and you'll probably see a scientist wandering around with a little detector, and it's doing this characteristic kind of like click, 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 click noise. Okay, now those clicks produce something that's known as a count rate. And a count rate is just the number of radiation counts that are reaching the tube and the detector per minute. Okay, so the more clicks there are, the more radiation is being detected, is essentially what it is. All right, now then, what we have to remember is that radioactive decay is entirely random, so we can't predict exactly which nucleus in a sample will decay next or when any of them will decay. We can't force it to happen, we can't predict it, we can't make it go faster, we can't make it go slower. It just is what it is. But you can find out the time it takes the amount of radiation emitted by a source to halve. Now, this is known as the half-life. Okay, so the time it takes for the amount of radiation to halve can be found out, and that is the half-life. And from the half-life, we can make predictions of the rate at which a source decays, and that is known as its activity. Okay, so half-life can be used to find the rate at which a source decays, that's its activity, and that is measured in something called becquerels. Okay, now handily for you, all you need to remember is that the symbol for becquerels is BQ, and that is just basically 1 decay per second. Okay, now the definition of half-life itself is that it's the time taken for the number of radioactive nuclei in an isotope to halve. Okay, so each time a radioactive source decays or a nucleus decays, it becomes stable, and this activity as a whole will decrease. So what that means is that the older something gets, okay, radioactivity decreases over time. So the older something gets, the less activity there is, the less radiation is being given out. Okay, now then you'll notice at the top here I've put maths and graphs because, of course, ladies and gentlemen, this is physics, so there's going to be some maths and some graphs going on. So, just going back to radioactivity a second, activity will never reach zero. Okay, so that's something to keep in mind if you are doing any kind of maths, if you are doing any kind of predictions of something, if you're doing anything to do with half-life and you get an answer of 0, you have not done it right. You have missed something out, you haven't understood the question, you've forgotten the principles of half-life. Okay, activity will never, ever, ever reach 0. All right, now then, some isotopes, the activity, all right, it will take just a few hours before nearly all of the unstable nuclei have decayed. See what I say there? Nearly all. So there will be some left, all right, whilst others can last for millions of years. All right, so it just depends entirely on the radioactive source and the radioactive nuclei that are involved as to the rate at which it will decay. Now then, half-life can be described as the time taken for the activity, and so the count rate to fall to half of its initial value. So there is some maths that are involved. Okay, so here's a question. The initial activity of a sample is 640 becquerels. Calculate the final activity as a percentage of the initial activity after 2 half-lives. Okay, and you're looking at that going, what on earth is that asking me? Okay, so I'll just let you digest that for a second. What the question's saying to you, all right, is number 1, the initial activity of a sample is, so you have a sample of radiation in front of you, and it's giving off a count rate of 640 becquerels, okay? Now then, 2 half-lives it's going to be going through, so that's your question. First thing you have to think about is, right, okay, I've got 2 half-lives, Okay, and I need to calculate the final activity as a percentage of the initial. All right, so there's a couple of bits of maths in here. Point 1 is you have to find out the half-life. Okay, and point 2 you have to do percentage calculation. Okay, so let's go to point 1. 1 half-life, okay, is basically you are taking this 640 and you are halving it, and that gives you 320. Okay, that's 1 half-life, but it's asking us for 2. So then it says another half-life. Now this is where it gets tricky and where students kind of like trip up and make silly mistakes. So you would go 1 half-life is 320, and then they go, right, so the next half-life is 0 because 640, they've gone 320 and then 320, right, so it's gone to 0. Okay, and that's where I'm saying, which is why it's really important the activity will never reach 0. That's a really common mistake. What you've remembered, what you've got to realise is that once this is decayed, you're now left with this. This is now the number that's going to halve. Okay, so that's at the end of 1 half-life. At the end of the second half-life, you've got 160. If you would go to the end of the third half-life, you'd end up with 80. You go into the end of a fourth half-life, you'd end up with 40. Can you see the pattern here? You are halving what you are left with every time. Okay, so after 2 half-lives, you're left with 160. So this is our count rate now, 160. Now then, the final part of the question is calculate the final activity as a percentage of the initial activity. All right, so percentage calculation, 160, okay, which is our current half-life after 2 half-lives. That's our current count rate, 160, divided by 640, which is our original count rate. All right, put those in brackets, you do that together, equals it, and then times it by 100, and that gives us 0.25, but then you should have 25%, because obviously. So 0.25 is this bit, and then you times it by 100 to give you this bit. All right, so that's a simple kind of question for the math side of it. Now, sometimes you will be given a graph, okay? And you'll be given a graph that's absolutely better drawn than mine is. Sorry if you can hear that meowing, my cat's trying to get in the bedroom. Okay, so activity. You've got activities up here. So this is our initial activity of 800. What is the sample's half-life? Okay, so remember half-life is a time frame. Okay, sometimes. All right, so you're actually having to work out what a sample's half-life is. So, dead simple. Our initial count rate is 800. So what is half of 800? It's 400. What you do is you go from 400, you read across to the graph line, you hit the graph line, you come down, and the half-life of this sample is 2 seconds. That is as easy as it's going to get. It's dead simple, that, isn't it? Okay. So you go half-life of 2 seconds. All right. Simple as that. Right, now then, that's all that we're going to talk about with half-life today. All right. It's quite a simple concept, really, but just this is key. Remember this, activity will never be 0. All right, just keep that in your head. All right, so what I'm going to do is I'm going to set you some work on Google Drive in your Google Classroom as usual, and I will speak to you all soon. Take care. Bye.